Hey everybody. In this video, we're going to talk about something new we didn't cover in physics class called a couple. So if you imagine you have two forces acting on a box, like say there's two people, one pushing from the left side, one pushing from the right side, but they're equal and opposite and same line of action. Right? So if you sum forces in the x direction, nothing's happening. Some forces in the y direction, nothing's happening. Some torque about any point you want, and you're going to get zero, right? So this is called equilibrium. If you have the additional condition that the momentum and the angular momentum is also zero, that's called static equilibrium. But now what happens if you have equal and opposite forces, say 10 newtons over here, 10 newtons over here, all right, equal and opposite. Some forces in x, nothing's happening. I'm using the same coordinates. Some forces in y, nothing's happening. Some torque about any point you want. Now this is not zero, right? So still equal and opposite forces, but different line of action. So together, these two forces form a couple. Couple means two, right? So that's why there's two. So this is a couple. Right? This is a couple. And then you can represent it, right? Just these two forces, you can just draw it as a single, like this way, like this. And I'll put a little m for moment by a couple, which causes torque. So whenever you see something like this, like you put over here, right, then that means there's a couple acting at this point. Okay, the weird property is you get the same torque due to a couple no matter where you define it in space. That's weird. So what I mean by that is if you have a force here, you say what's the torque due to that force about this point over here. That's different from if I pick another point like over here, right? R cross F, R cross F. But if I say here's this couple, what's the torque due to that couple about a point here? And it's something. I pick another point somewhere else in space, like over here. I compute the torque due to the couple. It's the same. So that's weird, but useful. Okay, so let me jot down what I said. Okay, so here's an example. So let's say if you take a look already, look, equal and opposite forces, different lines of action, right? That's a couple right here. Equal and opposite forces, different lines of action. That's another couple. So what happens is, let's say I pick a point here, like point A. What's the torque due to this couple about point A? And what's the torque due to this couple about point A? So the torque about point A is, I'll just do the magnitude, right? It's 9 feet times 20 pounds, right? So that's out of the page. So positive, right? Positive. So 9 feet, 20 pounds. positive. 0 times 20 pounds, right? So that's 0. And then about point A, see this lever arm is 2 feet times 30 pounds, which is going to go counterclockwise, right, which is positive. So plus 2 feet, 30 pounds. And then see this lever arm here is 5 feet. And that will be going clockwise, which is negative. So minus 5 feet, 30 pounds. All right, so this is 180. And this together is negative 90. I'll just change this to a minus sign. Okay, so this is the torque due to this couple. This is the torque due to this couple. So my claim is I pick some other point in space, like over here. What's the torque due to the couples about point B? Right, so about point B, see this lever arm, 5 feet times 20. 5 feet times 20, positive. And then here to here, 4 feet times 20, also positive. Right, so right here, 180. And then about point B, 0. And then here, 3 times 30 going clockwise, so negative. Same, right? Negative 90. How about I pick another point in space, here, C. What's the torque due to this couple about point C? So for this one, 0. From C to here, that's 9. So 9 feet, 20 pounds, and that's positive. And then about point C, for this, 0. Here to here is 3, and that's going clockwise, so negative. Right, again. So, right, it doesn't matter where you pick your point. The torque due to these couples is the same. So you could represent each couple like this one is 180 going this way. And then this one is 90 going this way due to B. And then again, you could move these wherever you want. It doesn't make a difference. Okay, let's try a 3D example this time. So let's say compute the torque due to the couple about wherever you feel like. So I'll let you try it. Well, let's make note that the unit vector from B to A is right, and then the unit vector from C to D is from C to D, 6 minus 3, so 3. Right, so these are equal and opposite, right? Just let me jot that down. Right, these are equal and opposite. So they form a couple. And then you just try it. Like, try and compute the torque due to the couple about the origin. Right? Then that would mean from the origin to B cross this vector plus from the origin to C cross the other one. And this is correct. But because you can compute torque due to a couple about any point you want, what if you did it about point B instead? Right, then the torque from B to here is just 0. So you would really only need to compute from B to C cross this, and then you're done. Right? What if you compute the torque about point C? The torque due to this force about point C is 0. So you really only need to go from C to B cross that force. Right? So, I mean, any of these three, they're all the same. But if you know that the torque due to a couple is the same about any point, I would rather do less effort, right? Do one of these instead of this. Okay, so new concept, couples. All right, thanks for listening. I'll see you on the next video.